like to do today is to talk a little bit about infinite geometric series, all right? And let's look at an example. And in fact, let's go back to an example that we looked at last time in terms of the sequence. Let me look at 1/2, comma, 1/4, comma, 1/8, comma, 1/16, and so on, all right? Now here we have an infinite sequence, which we considered last time. And let me associate with each one of these terms, as we have before, another sequence, which I'm going to call S sub 1, comma, S sub 2, comma, S sub 3, comma, S sub 4, and so on, so that associated with S sub 1 then is going to be the sum of the first term, which is simply the number 1/2. With the second term, S sub 2 is then going to be 1/2 plus, let me rewrite this simply as 1/2 the quantity squared, okay? And then what? S sub 3 we may write as equal to 1/2 plus 1/2 squared plus 1/2, what would this be? 1/2 cubed, all right? And so on in this fashion, and we can continue this on forever. Is that right? Now, this sequence we give a special name to it, in which we think of it as a sequence of partial sums. Isn't that right? We're never going all the way out to the last one because there is no last one. So let's call this a sequence of partial sums. All right, a sequence of partial sums of an infinite sequence. Now, the question is, well, let's in fact write that term S sub n, which is going to be what? 1/2 plus 1/2 squared, and so on, plus 1/2 to the nth power. Is that right? Now, what we are interested in is asking ourselves the question, does the series that we form from the original sequence, 1/2 plus 1/4 plus 1/8 plus 1/16 and so on, does that converge to some number? In other words, does the limit exist? And I think to answer that question is the same as to answer the question, does the limit of, let me write in the word, does the limit of S sub n as n goes to infinity, okay, does this exist? In other words, does this go to some number, let me call it capital S? And from what we worked with last time, let's look at S sub n again in terms of our formula. This is a finite sequence now, and then we'll let n go to infinity and ask ourselves what happens, okay? So what's our formula for S sub n? The general term is what? A sub 1 minus, what then is our formula? A sub 1 times r to the n all over 1 minus r. Let's then just make our substitution. A sub 1 in our example here is what? 1/2 minus 1/2 times r. What is our number r? Our number r is 1/2, and this is all raised to the nth power divided by 1 minus 1/2. Is that right? Which in fact we may factor out of the numerator the number 1/2 using our distributive property. We have left what? 1 minus what? 1/2 all raised to the nth power divided by 1 minus 1/2 is 1/2. I think it's a positive 1/2, and 1/2 divided by 1/2 is a name for 1, so we're left with 1 minus 1/2 to the nth power. And if you remember, this is what we developed last time. Now the question is, does the limit of S sub n, namely of this thing, let's write this down, does the limit of 1 minus 1/2 to the nth power as n goes to infinity, does this number exist? And what did we say about this number in our last lesson? This then is equal to, what was it equal? Well, 1/2 to the nth power was equal to 0. As n goes to infinity, 1/2 to the nth power is equal to 0. Therefore, the limit of 1 minus 1/2 to the nth power goes to 1. Okay? Therefore, what is our conclusion about the series? Let me write it using our summation symbol of what then do we have there? 1/2 to the, let me call it the kth power, where k goes from 1 to infinity. This number is equal to what? This summation, this infinite series that we have here goes to what number? It converges to 1, okay? And in fact, the limit does exist, and it's equal to 1. We have here, of course, an example of a geometric series, isn't that right? And let me just call this heading here, well, let me just refer to it simply as an infinite series, in which the example that we have here is certainly geometric, and this is a case in which it does have a limit, and therefore the series converges to that number 1. Well, let's look at a second example, and in fact, let's try to generalize this idea a little bit. Let me talk about any sequence now, the pattern a sub 1, comma, a sub 2, comma, a sub 3, and so on up to some a sub n, comma, and so on. Alright, here we have an infinite series now, an infinite sequence rather, and associated with each one of these terms, again, let's write that it's the same name, and what then do we call this? This is called, what do we have here? We just gave this a name in our first example here, in which it is called a, what? A sequence partial sum, alright? A partial sum. Every time you stop somewhere, that's simply a part of the total summation of that infinite series, is that right? So that associated with S sub 1 is the first term A sub 1, S sub 2 is the sum of the first two terms, and so on. S sub n then is one of the first n terms of the given sequence. Is that right? Okay? Now, what are we saying? I think that what we are saying is that if the limit of S sub n as n goes to infinity exists, in other words, if this limit is equal to some number, let's call it S, alright, then the series that we started with of the pattern, let me call it a sub I, where I goes from 1 to infinity. Now notice up here on top we're going from 1 to infinity. Let's make this into an infinite series. Is that right? And if the limit of the partial sums for n as n goes to infinity exists, is equal to some number, right, if indeed the sequence itself is converging, then the series which is formed from that sequence must also converge. Is that right? That we're saying? Then this series converges. And in fact, what number is it going to converge to? It converges to S, to the same number S. Okay? Let's look at another example, and perhaps if we were to look at an example or two of series that do not converge, perhaps that will make it more meaningful for those that do. For example, suppose we were to take, well, let me just go right to the series, 2 plus 2 plus 2, and so on forever. All right? And let's just continue this on. And here we have certainly an infinite series that we've just written. The corresponding sequence that we can form, which is the sum of partial sums, the sequence of partial sums, S sub 1 is equal to what number? 2, which in fact, let me just write as 2 times 1. S sub 2 is, we know, the sum of the first two terms is 4, which I may write as 2 times 2. S sub 3 is, what, 6, which we may write as, well, let me just set up a pattern here, what, 3 times 2. Perhaps I would rather rewrite this as, well, let me just keep that as 2 times 2, 2 times 3. S sub 4 then we know is 8, which I may write as, what, 2 times 4. And continuing this on down to some S sub n, I may write S sub n as equal to 2 times n. Okay? Now the question is, does the limit of S sub n as n goes to infinity, looking at our term here, which is 2 times n, does this limit exist? Does this go to some number? As n gets bigger and bigger, does S sub n, the limit of S sub n as n goes to infinity, does that converge to a number? And what does your intuition tell you? And I think you would say that the answer is no. Does this thing equal to some number S? And our answer is no. Therefore, what's our conclusion about the series which is formed of the pattern, let's call it 2I, where I goes from 1 to infinity? Therefore, this series must do what? It diverges. D-I-V-E-R-G-E-S. The series, the corresponding infinite series, then must diverge because the limit of the sequence of partial sums does not have a limit, okay? In other words, it does not converge. Let's look at another example and see if perhaps we can't get a little bit more insight into this. Suppose we look at, say, 2 comma, negative 2 comma, 2 comma, negative 2, and so on. And then let's form from that the series. This is going to be the sequence, and then the series will be what? 2 minus 2 plus 2 minus 2 plus 2, and so on. And in fact, let's then also look at the sequence of partial sums. The sum of the first term is simply 2. The sum of the first two terms is 0. The sum of the first three terms is 2. The sum of the first four terms is 0. again, I think we see the pattern that is establishing in which our sequence now of partial sums is 2, comma 0, comma 2, comma 0, and so on. And the question is, what then can we say about the limit? Let me write it that way, does the limit of s sub n as n goes to infinity exist? Does this go to some number? And does it go to some specific number as n goes on forever? The summation of this is it coming in on a specific number here as we continue on out there? And in fact, our conclusion here is no. Therefore, what then can we say about the series of the pattern? Now let me see how we can write this. Let me write it as negative 1 raised to the I plus first power times 2. And where I goes from 1 to infinity. And let's just look at this in a second. But what is our conclusion about this infinite series? Since the sequence of partial sums does not have a limit, it does not go to a number, what then is our conclusion about the corresponding infinite series? It must, Charles, it must diverge. It diverges. Okay. Let's look at this, by the way, and to make sure that we have the same sequence here, the sum of the partial terms here, of the sequence. Negative 1 raised to the 1 to the I plus 1 power. When I is 1, 1 plus 1 is 2, and negative 1 squared is 1, and 1 times 2 is 2, and sure enough, that's our first term. When I is 2, okay, we have 2 plus 1 is 3, and negative 1 to the third power is negative 1 times 2 is negative 2, and sure enough, we then will have the sum of the first two terms. Is that right? And I think you would agree that this summation symbol here, written in this pattern, gives us our infinite series that we have right here. Okay? Again, notice that since the limit of the sequence of partial sums does not exist, then our conclusion is that the corresponding infinite series must diverge. Okay? Let's look at let's try to generalize all of this with respect to our geometric series, all right? Let me call this an infinite geometric series and see what we may say about that. And again, let's form let's go back to the original sequence, which is of the pattern a sub 1, comma, a sub 1 r, is that right? Comma, a sub 1 r squared, and so on out to what? A sub 1 r to the n minus 1, all right? Comma, and in fact, since this is an infinite geometric series, we'll just continue these dots. Here we have then the corresponding sequence of partial sums, s sub 1, comma, s sub 2, comma, s sub 3, and so on, to some s sub n, and continuing it on forever, okay? In which we know that s sub 1 is the sum of the first term, s sub 2 is the sum of the first two terms, and so on. S sub n we know is equal to what? The sum of the first n terms, which is of the pattern what? A sub 1 plus a sub 1r plus, and so on, and then what then is the nth term out there? A sub 1 times what? R to the n minus 1. Now, notice here we can't put another plus on with some dots because this is the s sub n term. Is that right? Now, the question is, again, does the limit of s sub n as n goes to infinity, does this limit go to some specific number? In other words, does the limit exist? And let me say, does it equal s, or is it equal to s? And I think we're going to have to look at our nth term here and say to ourselves, well, it's going to depend. And it's going to depend on what numbers, do you think? Just looking at our formula here, do you think it might depend on what the number a sub 1 is? It might. I think it might. And in fact, certainly it would also depend upon what number? On r. Now, let's actually write that down. This depends on a sub 1 and r. And I think what we have to do is to look at various cases and see what happens, okay? So let's come up here and let's talk about case 1. I'll just call this one the first case, in which let's let a sub 1 be equal to 0. Right? And we really don't care too much about r. In that case, then, s sub n is equal to what? The first term is what? a sub 1, which is 0. What's our second term? Plus 0. What's our third term? 0, and so on. What's our nth term? 0. Well, then the question is, does the limit of s sub n, as n goes to infinity, does this go to some number? And just looking at it, well, what's the sum of all those terms? That's going to be equal to 0. So does this limit exist? Yes, and in fact it's equal to 0. Therefore, our sum of what? We may write this as, how may we say this? We have here 0 times, right, r to the k minus 1, where k is equal to 1 to infinity. All right, what then can we say about this corresponding infinite series? It certainly will what? It will converge, and in fact it will converge to what number? It will converge to 0. This is a very straightforward, very simple case that we are considering here, but I think it's certainly one for us to look at. Most of the time, of course, we will not have a sub 1 to be 0. So let's take that as another case, call it case 2, in which a sub 1 is not 0, and let's pick out some number r. Let's let r be equal to 1 in this case, and see what happens, okay? Well, let's then see if we can't go right to s sub n. Now, if a sub 1 is not 0, and if r is equal to 1, what's our first term of s sub n? A sub 1. Plus, now r is 1, so what then is our second term? A sub 1. Plus, what then is our third term? A sub 1, and so on, out to the nth term, which is a sub 1. Now again, let's ask ourselves the question, does the limit of s sub n, as n goes to infinity, does this limit exist? And looking at our series here of partial sums, the sequence of partial sums, as n goes to infinity, I think you would conclude what? Does this thing equal some number s? And your conclusion is, I don't think that it does. I think we would conclude that, all right, whatever this number is, suppose, for example, we take the first example of 2. 2 plus 2 plus 2 plus 2 and so on forever. We have just concluded diverges. Therefore, our conclusion about the corresponding infinite series, let me write it as a sub I, where I goes from 1 to infinity. What is our conclusion about this? It diverges. It diverges. Okay, very nice. Well, let's look at another case. Call this one case 3. And in this case, we'll a sub 1 again. Let's take not to be 0. And let's take the number r to be negative 1. Okay? Now let's look at what s sub n is going to be like. Now what's the first term of our sequence will be what? Well, it would be what? I believe it's what? A sub 1 is our first term, right? Our second term is a sub 1 times r, where r is negative 1, so our second term is going to be what? Negative a sub 1. Our next term is what? Plus a sub 1, and the next term is minus a sub 1, and so on, all the way out. Is that right? On forever, in which we're going to be alternating in this fashion. Well, let's write it in terms of s sub 1. Let's just go vertically for a while and see if we can establish some pattern here. What's the sum of the first term? A sub 1. What's the sum of the first two terms? 0. What's the sum of the first three terms? A sub 1. What's the sum of the first four terms? 0, and so on. And finally, the s sub n term I may write in terms of what we have there. Let's just repeat that. A sub 1 minus a sub 1 plus a sub 1 minus a sub 1, and so on in this pattern. Now again, the question is, does the limit of s sub n, as n goes to infinity, does this exist? And looking at our example over here, in fact that's the reason why I selected this example originally. Here we have 2 minus 2 plus 2 and so on, in which what was our conclusion here? That this one certainly diverted. So the question is, does the limit of this equal some number, s? And our answer to that question is no. Therefore, the corresponding infinite series, now let's see how we may write this again. Let's write it as negative 1 to the I plus 1 power times a sub 1, where I goes from 1 to infinity. What's our conclusion about the series? It diverges. Okay. Now this is perhaps a rather long and involved way of getting around this infinite geometric series, but I think we have to actually consider each one of these cases in order to decide exactly what happens. Let's look finally then at another case. Let's call it case 4, in which a sub 1 is not 0. And let me now take the absolute value of r is not equal to 1, which indeed takes care of the two cases that we have just considered. When r is 1 and when r is negative 1 are now excluded from this situation. Okay? Well, when that is the case, if you remember our formula for s sub n, which we developed a few lessons ago, was equal to what? In terms of a sub 1, again, we're repeating this formula. What is it equal to? A sub 1 minus a sub 1 r to the n all over 1 minus r. Now, what I'd like to do is to look at this and look at it from a slightly different point of view. And what I mean by that is I'd like to separate this into a sub 1 divided by 1 minus r minus, in fact, here we have a sub 1 over 1 minus r times r to the n. Does everyone agree that this is still, that this is equal to this? Okay? Now, let's consider the case in which, if the absolute value of r is greater than 1, right? Here, the absolute value of r cannot be equal to 1, so let's then consider the case where it is greater than 1. Now, if the absolute value of r is greater than 1, let's look there at the limit of r to the nth power as n goes to infinity. Now, if this number is bigger than 1, the absolute value of r raised to the nth power as n goes to infinity, does this go to some number? Will this converge to some number? And I think you will agree that that will not converge to some number s, call it. Okay? Therefore, what then can we say about the limit of s sub n of the original sequence, in the original series here of partial sums? What then can we say about this? Does this go to some number? And I think you would agree that this does not go to any number s. Now, therefore, what can we say about the infinite series of the pattern a sub 1 times r? Let me now use the letter k minus 1 as k goes from 1 to infinity. What's our conclusion about this one? This is the corresponding infinite series, and it then diverges. Okay. So when we have the absolute value of r greater than 1, the corresponding infinite series, geometric series, diverges. Well, what else is left? What other case can we consider? If what? If the absolute value of r is what? Is less than 1. Now, when that is the case, then let's look at the limit of the absolute value of r raised to the nth power as n goes to infinity. What do you know about that limit? This is the kind of situation as we had in the first example, way over there, in which we had 1/2 to the nth power. And what is the limit of the partial sums of r to the nth as n goes to infinity and r is to an absolute value less than 1? What's your conclusion about that, Tom? It's equal to, well, just here, suppose we had 1/2 to the nth power. And that's getting closer and closer and closer to what number? Not to 1 in this case, but to 0. Is that right? It's getting closer and closer to 0. Therefore, what can you say about the limit of s sub n as n goes to infinity? Well, let's come back here and look at our formula. Now, we have broken it up into two parts, and for the case that we're now considering, here we have r to the nth power, where this number goes to 0. So 0 times this number must be equal to what? Equal to 0. Therefore, what then is the limit of s sub n as n goes to infinity? What then is that equal to? A sub 1, Malcolm, over 1 minus r. So this limit then is equal to a sub 1 over 1 minus r. Well, if that's what the limit of the sequence of partial sums is, what then is our conclusion about the infinite series of the pattern a sub 1 times r to the what? N minus 1. Let me now call that k. K minus 1, where k goes from 1 to infinity. What then can we say about this infinite series? It converges, certainly. This series converges, and on what then does it converge to? It converges to the number a sub 1 divided by 1 minus r. And it's a very simple little formula that we're looking at here. So for those cases in which the absolute value of r is less than 1, right, that infinite geometric series converges, and in fact it converges to simply a sub 1 divided by 1 minus r. Well, I think that's all the time that we have today, and let me give you your homework assignment. this will be assignment